some of my family members here. So welcome everybody as you sign in. If you would like to use the chat function at the bottom, you can just click, you hover over the lower part of your screen here, you'll see a button that says chat. If you hover over that and click, you can put in a note that so we can see where you're calling from. All right, and so I think we'll go ahead, John, and we'll get started. If you want to, let me just introduce myself. I'm Jim Madsen. I'm the Executive Director of the Wisconsin IceCube Particle Astrophysics Center. And we've got John here and Yuya, who are what we call the winter rovers. They're spending 13 months at Antarctica, keeping the IceCube Neutrino Observatory running so we can collect all this exciting data. So with that, I think we'll start the presentation.
Sounds good to me.
Thank you. Okay.
All right. So, hi everybody. Let me introduce myself. My name is John Hardin. I'm one of the IceCube winter rovers, and I'm sitting here with
Yuya,
who's the other IceCube winter rover. So we wanted to give you a short presentation, a little bit about life down here, and a short bit about the science, and then there'll be a chance to ask questions at the end about anything you want to ask about. So with that, let's get started. This first slide here talks about how we get down to the South Pole proper. The Antarctica is a big continent, and it's pretty hard to get to. There aren't many runways down here. So we need specialized planes to get onto continent and to get around on continent. The upper left, you see a Basler, a DC-3. It's used just for passengers. It doesn't carry very much else, but it's useful when it's especially cold and harder for the big plane to run, the big planes. One on the right here you see is an LC-130, also known as a Hercules. This is what does most of the lift from McMurdo, which is a station on the coast of Antarctica, to the South Pole proper, which is in the interior. And the Hercules, is, the name implies, carries quite a bit of cargo and passengers, if you like. Just on the bottom here, you see the PAX terminal for the South Pole, which is just a box to keep the wind off of you. And then the picture in the lower right is Yuya and me just after we got to the South Pole, a few days. We went out to the geographic and took a good picture. So with that, next slide, please. The station itself. One of the things about the station that many people don't know before they come down here is that it's actually at 9,300 feet of elevation, and that's almost entirely ice between us and the bedrock. The physiological altitude, the altitude with respect to the pressure, actually varies between 10 and 11,000 feet. Because of the way the winds work down here, our pressure is often lower than where it would be on the rest of the globe. The trick with that is that you end up getting altitude sickness if you're not careful down here, at least when you first come down until your body adjusts. The air is about 2/3 of the density of air at sea level. So you have to be very careful getting on the treadmill for a week, or my sister, who's in med school, tells me 3 weeks total, really, to get all the way up. The station, we call it the elevated station because it's actually elevated. It's 65,000 square feet. It's very nice. And, a whole 50 of those are set up for each of the winter bedrooms. The winter bedrooms are great because they're bigger than the summer bedrooms. You can see there's 4 tiles across up there. In the summer bedrooms, we only get 3. So it's nice. Lower left, you can see the galley. Galley's a nice big meeting space. The food is delicious. This is a picture from the summer. We actually cover those windows in the winter so that we do not interfere with the cameras taking pictures of the auroras outside. And then we also use 450,000 gallons of fuel per year. And most of that, good 2/3, 3/4 of it, is actually brought here by tractor over land, not by the planes. It's called the Traverse. And this is a picture of the Traverse arriving. So next slide, please. We have all kinds of fun here. We play wiffle ball in the gym. It's a tradition to watch The Thing as soon as station closes every year. All 3 versions of it, in fact. I learned this year that the first version of The Thing was actually set at the North Pole. I tried not to be too offended by that. The lower left here, you can see a picture of me putting up the window blockers in the ICL. We'll talk about the ICL later. Again, to prevent too much light from leaking out and interfering with cameras. And then in the lower right is a picture of us having dinner just after station close. We all got together and had the real nice dinner. The galley said they did 4.5 courses. Zeke said he wanted to do 5, but that was too many last time. So 4.5 it was. It was delicious. So next slide, please. So this is more of the station. Upper left is one view of the station. That's the side of the station that faces into the wind. It's shaped somewhat like a wing to try to get the snow to whip around it. You can see a little bit of a hill of snow, but if you look carefully, you can tell that the station is actually elevated. The upper right, you see a picture of the geographic South Pole planting. So every year at New Year's, the geographic South Pole is resurveyed, and typically the ice is moved about 30 feet. And so it has to be put in a new location. The new pole marker is designed by the previous year's winter rovers. So this is pretty fun. This is the one winter rover from 2019 who was still here on New Year's Day 2020, and he did the planting because of that. Lower left is all the previous pole markers. Lots of fun ones. There's one of IceCube in there, and there's one of some other telescopes. Lower right is our power plant with 3 different generators. Generation is important down here. Any one of those generators can keep the entire station running, so we like to have redundancy and room for preventative maintenance. We also have a backup generator separated from this power plant, just in case, because heat is very, very important down here. Next slide, please. Let's see. There it is. The greenhouse. This is a new slide from last week, if any of you were here. We decided to put it in and get a picture of kind of what the greenhouse looks like. I promise you it doesn't look quite as yellow as the upper left picture implies, but this picture was taken when the grow lamps were on, and the grow lamps really like to mimic the sunlight to try and get the plants growing as much as possible. But how it works is it's all hydroponic. The Antarctic Treaty actually prevents us from bringing soil down here. It also prevents us from growing anything that isn't edible. So even the flowers that we grow in here are edible. The way it works is we plant the plants outside in what's called a rock well, if you're familiar with how greenhouses and hydroponic systems work. If not, it's like a dense mesh that has a little bit of nutrients and lets the roots grow and also brings water to them. Eventually, when they get good enough, we transfer them to the hydroponic system, and we put them in what's called preschool after they were in the nursery. And then when they get even bigger there, we pull them apart and we put them in their own individual hole. You can see the little holes in here. And then they get big. Most of what we grow in here is stuff that will get a good amount of flavor and has a lot of water. So we grow a lot of tomatoes, we grow some cucumbers, and then we grow a lot of leafy greens, like kale and mizuna, and chard, things like that. We also grow basil. You can see here is Anthony from our VMF. He's picking the basil. We have a pretty good herb garden ready for the galley to make fresh herbs and fresh seasoning. It's a good time. I volunteer down there once a week. So yeah, next slide, please. Here's Christmas holidays. So the holidays are during the summer down here. It's still cold, still below zero, but warmer than average. And the way the holidays work is the galley, again, goes all out, makes a multi-course meal. It's delicious. Everybody gets together. Now, there's typically 150 people or so on station around this time. You might be able to tell from this picture in the lower right that, there's probably more than 42 people in that picture, even though there's only 42 winter rovers. On the left, you can see dessert for Christmas. It was really good. She actually had some people come in and volunteer to make Christmas cookies, which made me pretty happy. I love making Christmas cookies. Then in the upper right, we see the gingerbread house competition, where people made a whole bunch of different gingerbread houses, and the winner is in the front here on the left. It's a picture of the station. So yeah, the holidays are fun. Thanksgiving was fun. It was real nice because, being away from family during the holidays isn't so fun. So having something nice to do down here was good. The weather down here. So the weather is very important, especially during the summer, but also during the winter, both for safety reasons and importantly for planes. Whether or not the planes can get in, get out, whether or not they're coming, it's hard. So in the upper right, you can see Yuya actually marshaling a plane, something you get to do while you're down here. The lower left, you see our summer meteorologist, David. And in the lower right, you see David launching a weather balloon. They launch weather balloons, I believe, almost daily down here. So it's pretty fun. So next slide, please. We have all kinds of other fun while we're here. Upper left, you see a tent. We learned how to use a survival bag. We are not likely to be out in the field down here unless we get very lucky. But it was still fun to learn how to use the tent and the stove and everything, keep ourselves alive. Then you see people doing the walk to Mordor in the next picture. It's where everybody watched the entire 3 Lord of the Rings extended editions on the treadmill the entire time. And then Yuya is, participating in a wise fashion in the walk to Mordor. Then Wisconsin, the university that is the headquarters of IceCube, was in the Rose Bowl this year. And so every year that Wisconsin has been in the Rose Bowl, we have actually had people down here, and there's been a sign at the pole saying "Go Badgers" and freeze whoever their opponent was. We did it again this year, which was all kinds of fun. Lower left, you see a penguin in a Carhartt. This is one of Yuya's projects. And the Carhartt, the big red, may be the iconic thing that people wear at the South Pole, but it is also very common for people to wear Carhartts. They're quite warm, and they're a little less bulky. And if you're just in and out all the time, they're really nice. Lower right here, you see me and Yuya at the edge of IceCube playing chess. That was a good day. There was a little bit of a time limit on how fast your hands got cold, though. Next slide, please. So this is sort of the end of summer. In the upper left, you can see the sunset over SPT. For some reason, Yuya chose SPT for the sunset rather than the ICL. SPT is another telescope down here. Then the lower left, you see package mail. We had a little bit of delays on our packages getting in, so we were very happy to get everything we had shipped to ourselves and everything our family had shipped to us in the beginning of February. And then on the right, you can see our vacation to McMurdo. The winter rovers are allowed about a week vacation to the seaside resort of McMurdo, and we take a Hercules to get there. This is the inside of the Hercules. You can see sort of the bags strapped in the middle and the people sitting on the side and the cargo way in the back. This is just how it works. It was a good flight, and it was a good time to be there. And then, yeah, this is sunset. This is sunset actually over the ICL. we have a little bit of a rivalry down here with the different telescopes. It was very pretty. We were very happy to see it. It's completely dark outside now. I think you said, are we full? We're out of twilight today, or are we out of twilight tomorrow? 12th. We're at the twilight of the 12th. By twilight, we only mean very technically twilight. It's detectable by telescopes. It's dark out there, at least when the moon's not out. The moon rose yesterday, and the moon's very bright because it was full. But when the moon's down, it is very, very dark out there. So next slide, please. Yeah, twilight, I mentioned it. The sun, because the way the sun works down here is it does a slow spiral up and a slow spiral down, such that it only rises and sets once per year. The twilight lasts an incredibly long time, like 2 weeks at a time. And you can get some great pictures while it's happening. This lower picture, that's actually the moon, it's not the sun, behind the ICL. You may notice the red lights on all the buildings. We leave those on for safety at night so that you can see the buildings from a long way away, and especially if the wind picks up and the visibility goes down. So next slide, please. Auroras. Ah, yes, wonderful pictures of the auroras. Yuya and I were extremely excited the first time we saw an aurora. We were actually out shoveling snow at the ICL, which, yes, indeed, you still need to shovel snow at the South Pole. And we went outside and we looked up, and there was an aurora just up in the sky. And since then, they've been, almost every day that it's been clear, you've been able to go outside and see something. They're beautiful. They're just really nice. You get different colors. In some of these pictures, you can see the Milky Way in the background. It's been really fun down here. It's been really exciting to see everything. All the stars and the astronomy as well. It's cool to watch. So yeah, next slide, please. So yes, the South Pole. We divide the area around the South Pole into different sectors. There's the dark sector, dark meaning no radio communication, which contains IceCube Laboratory, contains the South Pole Telescope, and it contains the background imaging of cosmic extragalactic polarization, which is actually a verb. It's not a name, but we call it BICEP anyway. It's not a noun, but yeah, we call it BICEP anyway. There's actually a couple BICEP telescopes that go down here. BICEP and SPT are different from IceCube in that they're looking at the cosmic microwave background in a couple ways. They have a much cooler looking telescope. In the lower right here, with the summer grad students, John and Matt, you can actually see them in front of SPT. It's a gigantic dish. It's cool what it can do. The IceCube lab, our telescope is entirely under the ice, but our computing center sits on the top floor of the ICL, which is the building in the lower left. And we spread out over a cubic kilometer. You see SPT in the background there. The IceCube telescope strings actually go behind SPT from that picture. And that's some idea of how big SPT is in the lower right. The other two science sectors are the quiet sector, where there's not supposed to be any vibration, and the clean air sector, where you don't want any sort of emissions. We keep it upwind of all of the power plant and heavy machinery and all that. It's the cleanest air in the world. It's where they can monitor carbon and all sorts of other properties down there. Next slide, please. So yes, I mentioned the ICL. We have 86 strings. We'll see a picture of that shortly, but we contain computers for all of them. Our computing infrastructure is pretty huge. We have 18 racks of servers and data acquisition computers. We call them DOM hubs. You can see a picture down here. In there is some custom hardware that will receive data from one string. So one string has 60 DOMs on them. It's a digital optical module. You can think of them as the pixels of our detector. And they image in 3D. And this collects one of the 86 strings. So we actually have 86 of these plus some spares sitting in the ICL. And then we have an entire set of computing on top of that. Lower left, you can see the ICL is not just for computing. The lower floor is sort of a clearinghouse for the different sorts of cargo we need. It's also a place where we do other experiments, both supported for the IceCube upgrade and for other related experiments. We have an ice core experiment that monitors how clear the ice is, independently of our own monitors. So we do all sorts of things out of the ICL. It's about 2/3 of a mile from station 2. So yeah, next slide, please. Yeah, we're on to IceCube science. Let's go. So this is a little bit of a 3D view of what IceCube looks like. I mentioned we're about 9,300 feet above the ice, and the ice goes almost all the way to sea level, down at bedrock. And the strings themselves, the DOMs, are these little black dots, and they go almost all the way to bedrock as well, and they come only not even halfway up the ice. So the detector is way far down there, very, very far down. And we want this because we want it to be very dark down there. So this is an idea. You see where each of those strings are up there. This is about how it works. Each of those is a pixel, and it picks up light from what I will describe in the next slide. So the way this works is neutrinos are almost never interact. They were the last particle to be, in the standard model, to be directly detected, and that's because they are so hard to get to interact. When they do interact, what they do is they turn into a charged particle. And charged particles, they, on the other hand, they very commonly interact. So the neutrino only interacts with weak force, which is very weak. Charged particle interacts with the electromagnetic force. It's the force that makes light. Now, they produce something called Cherenkov light. Cherenkov light is a little tricky, but it's not too complicated to understand. You may have heard that you cannot go faster than the speed of light, but that's actually only true in a vacuum. You cannot go faster than the speed of light in a vacuum. You may also have heard that light travels slower in materials, like water. So if you've ever stuck a pencil in water and seen it bend, it's because the light is moving slower in the water than it is in the air. Now, there's nothing stopping a charged particle from going faster than the speed of light in water, or in this case, in ice. And when it does, what it does is it actually produces the equivalent of a sonic boom. It makes an optic boom. It makes a cone of light. And that light is what we detect in our pixels, our DOMs. This is a picture of a DOM in the bottom left here. These things are maybe a foot, foot and a half in diameter. The entire lower hemisphere is dedicated to being a pixel. We need to be very sensitive, and we need to see a lot of the light. So that's why we do this. The upper part is a little bit of computing that allows it to talk to the surface and also decide if it's interesting enough to talk to the surface. You can imagine our bandwidth is actually not very high, over a mile of a single piece of copper. And we need to be very sensitive. So, yep. Next slide, please.
All right, we'll do that quickly, John, and then we'll move on to Q&A, okay?
Okay, we'll do one more about the science, and then we'll move on to Q&A. I'll be quick.
Yep.
So what do we actually see? This is our readout from the detector. You can see these, each of these spheres that's colored is a DOM that saw light. The size of the sphere is the amount of light it saw, and the color is when it saw the light. So what's cool is we get different patterns. And what's really cool is, like in this upper one, is we see that the particle appeared in the middle of our detector, as far as we can tell. And the reason that's happening is the neutrino came into our detector, it didn't interact, and then it became an electron, and it made this boom of light. Now, the neutrino is the only particle we know of that can get into our detector without us seeing it on the edges, which is how we know this is a neutrino, which I think is really cool. I think it's really fun to be able to pick this out by eye. In the lower left, you can see a little bit about a muon neutrino. This one is coming up through the Earth, which is how we know it's a neutrino. Neutrino is the only particle we know of that can get all the way through the Earth and to our detector before it makes a muon. The muon flies a little bit further through the ice, and that is how we can get the direction out of it. So both of these you can kind of pick out by eye, and it's fun to do. But I'll leave it at that. We really use computers to actually do the analysis on these. So yeah, with that, let's go into questions, and questions about anything. Life at the South Pole, IceCube science, whatever you want to talk about.
Yep. So if you have questions, you can type them in in the Q&A or in the chat box. So, so the first question we have is, what kind of problems do the winter rovers have to fix at the ICL?
So the ICL has all kinds of problems. When we have to go out, typically what has happened is there's a hardware issue with the dom hub. Recently, one of the repaired patch cables had become frayed and was causing one of the DOMs not to work properly, and we had to go replace that. Sometimes we'll lose some of the timing cards that exist in the DOM hubs, and those have to go be replaced. We used to have a much bigger issue with the DOM hub power supplies, but this summer we replaced most of them and they've become much more stable. But when that happens, we have to go out and replace that to get the entire string back. Otherwise, we've lost the string.
Okay. We don't have any other questions at the moment. If you would like to ask some questions, feel free to enter them either in the chat box or in the Q&A. Maybe you could give us an idea, what's the temperature right now? And
today,
what's the range?
I think it's minus 85 today.
Yeah.
It's been, minus 60 or so for a while. Yeah, it's minus 85 and the wind chill is minus 125 at the moment.
And have you been out recently?
We went out yesterday.
Did you?
We had a couple of maintenance tasks at the ICL that we needed to do. One of the things we did is we measured the tilt of the ice, and that requires plugging in directly at the ICL.
Neat. Okay, we have another question. What do the other winter rovers do at the station?
People do all kinds of stuff. We need everybody down here to do everything. We have 3 different people who work in the galley. We have one person here who works as a steward. We have several people down in the vehicle maintenance facility, the VMF. We have, I think, 3 people in the power plant. We have a whole bunch of people doing all kinds of preventative maintenance. We have carpenters. We have someone who works at the rod well. The rod well is where we get our water. We have the station manager. We have about 10 people doing science, like Yuya and me, 10 or 12. We have a dedicated machinist. We have weather. We actually keep a dedicated meteorologist all winter. We have everybody. I'm hoping I didn't forget anybody going through. I haven't listed 42 people, but a lot of those jobs are done by more than one person.
Yeah, I think it's neat, as you say, it takes a really varied team in order to be able to do this type of science. And if it was all physicists, we'd be in big trouble, right?
Yes, we would. Physicists are not very good at keeping themselves alive.
Yeah. Okay, so we have Marla from Bunker Hill, Illinois wants to know, how are your eyes protected and can you wear contacts?
So I wear contacts. When I came down here, I was really worried that it was going to be too dry. I believe I think we're the driest desert in the world. If we're not, we're the second driest desert in the world. But I think we're actually the driest desert in the world. And I was concerned that my contacts would dry out, but they do not. My contacts work real well. When we go outside, if we wear goggles, typically. I've found that if you just make a nice slit between your hat and your balaclava, if it's not windy, your breath will keep your eyes warm, and you don't run into the issue of your goggles fogging up, which is important. You can also see the stars in the aurora better, which is important to me. If I try to wear glasses outside, they fog up immediately. So that's an issue.
Okay. We'll stick in the chat box. Barb wants to know, how many neutrinos do you see in 24 hours?
So this is a tricky question. We see a ton of neutrinos that we would classify as background. So we see a bunch of what are called atmospheric neutrinos. That is high energy neutrinos that were produced in the upper atmosphere by high energy cosmic rays. Now, lots of people are very interested in high energy cosmic rays, but it's not what IceCube was built for. I think we see one of those every 4 minutes. So in 24 hours, we see, what, 60 times 6, 360 of them, 300, 400 of them. The neutrinos we're very interested in, however, are called astrophysical neutrinos. They're neutrinos that come directly from a black hole or directly from a neutron star, or even better, a supernova, although I think we'd have to get pretty lucky to see one of those down here. We see an astrophysical neutrino about once a month. Which is why it's important we keep our uptime as high as it is. Our uptime is like 99.8, 99.9. And we want to never miss a neutrino if we can help it.
Okay. Hey, John, do you think you have enough bandwidth you can turn your camera on?
Yeah, let me see. Let's find out. The host has stopped my video.
Okay, I'm going to make you the host and see. And then you should be able to turn your camera on.
There we go. That works.
Great. There they are.
Yep. Hey.
Those are the two that keep our experiment running. Very good. Okay. This next question, I'll paraphrase a bit. How did you find out about IceCube?
So I actually found out about IceCube through a friend of mine. When I was in grad school, I worked on a different accelerator-based experiment called GlueX. And I found out that IceCube was a thing, and I found out that neutrinos weren't quite as uninteresting as I originally thought when I entered grad school. And so I started talking to him and his advisor, and I was able to join the experiment. I was very happy.
How about you?
How did you find out?
So before coming here, I was working as a postdoc in IceCube group in Japan. So that's how I got this position.
Okay. So let's see. We'll go back to a question about life, living and working down there, and then come back to IceCube. But they wanted to know exactly, how do you get water?
It's a good question. So we get water through a technique called a rod well. The way the rod well works is we bore a hole in the ice down past the top of the ice, which is not very solid and is very porous. And then in there, we send heat, and we also pump out water. The reason we do it this way is that we don't want to lose heat. We want to melt ice as efficiently as possible. And as it turns out, this may surprise you, but ice is not a very good thermal conductor. So the same reason igloos work is why the rod well works. We just send a big hot, I think it's a piece of brass down there, and it continues to melt ice and melt the water. And it makes this big bulb in the ice. And then we just, there's a bunch of liquid water up there that we pump out to pull water out. It's supposed to be the most efficient way to get water out of ice.
Yeah.
If we did it at the surface, we'd always be losing heat to the air. But this way, we're not losing heat to the air. And that's how we keep everything melted without wasting electricity.
Okay. We'll jump to a construction question. How were the DOMs placed in the ice? They want to know if they were drilled to be placed in, how long did it take to drill?
So the way it works is they use a hot water drill to go all the way to the bedrock. And then they have, I think, what is it, 36 hours, 48 hours
On that
before the drill, before the hole will close so much that the DOMs cannot get all the way down. So they drill all the way to the bottom, they pull it out, and then they feed in the cable that contains the DOMs. I'm told that by the end of it, they were able to get an entire string in 12 hours, which I think is pretty impressive.
Yeah, I think
The drill
yeah.
is all done in the summer, as far as I'm aware, or was. But IceCube is actually gearing up for an upgrade pretty soon. And they had a drill team down here this summer preparing for hopefully next summer, although that may be in a little bit of flux now. But there will be an upgrade coming soon that needs to be, more drilling needs to happen.
Yeah, I think the typical time was about 12 hours, but there were some crews that could do it as fast as 6 hours. So.
Oh, wow.
Yeah.
Just drop them in there, free fall.
Exactly, yeah. And I don't know if I know the answer to this. They want to know how many countries do people apply from to be winter overs. So I know we've had Germany, Japan now, the US, Belgium, I believe, right? But do you remember in your cohort, maybe you could talk a little bit about, did you have 6 people that you went through with in the interview process?
Yeah, so I don't know about the actual application process, but I know at the interview there's about 6 people.
Right.
I think normally they do it in 3 and 3 in the in-person interviews, but I think ours ended up being 4 and 2. And I think we had somebody from Germany, Japan, and US.
Okay. Yeah. Then there was another question about the water. Do you have to filter it or treat the water?
We do not have to filter the water. This is the cleanest water in the world. You can actually go downstairs and pull it straight out of the tap and get 50,000-year-old water if you want. Now, the one thing we do have to do is we actually have to add minerals to it. It is not super great for humans to drink water this pure. It will dilute your minerals in your body. So they do add minerals to it to try and prevent that from happening.
Okay. So I'll be interested if you know the answer to this one. Do you know anything about the timing for the next astrophysical neutrino?
I got the inside scoop now.
Yeah.
So unfortunately, no. The way we model this is with actually a Poisson distribution, which means we have no idea about the next likely timing of the next astrophysical neutrino. The way a Poisson distribution works, just as a little bit of a statistical fun fact, is the most likely timing for the next astrophysical neutrino is right now. And it's always right now. But most likely doesn't mean all that likely in this context.
Yeah.
Because it's an exponential decay.
Right. We tell you that so you stay, engaged, right?
Yes.
Okay. And here's a question about history. Is there anything left from the original Amundsen and Scott expeditions at the South Pole?
Yes, I believe there is. Behind us here, we have all sorts of different memorabilia. This is a book, I believe, written by Amundsen. The tent, we think we know where the original Amundsen tent is, but it's well under the ice by now. Our current winter manager is actually a big collector of this sort of stuff. So he has a whole bunch of different fun things. He has a teacup actually from the Terra Nova Scott expedition. And he has a piece of the mast from Shackleton's boat, Shackleton ship.
Oh, very cool.
So there's that, and I believe we have in a few places around here we might have a letter or something.
All right. And then this question, you can maybe talk a little bit more about seasons and day and night. It says, do you have any sunlit rooms?
Do we have any what rooms?
Sunlit rooms.
Sunlit.
Yeah.
Not in the winter.
Yeah.
So there's no sunlight in the winter. We don't have, you may, if you're asking about, do we have a room that, you can go and pretend there's sun, the closest thing we have is the greenhouse. Those full spectrum lamps are pretty good. We also have happy lamps down here, a whole bunch of full spectrum light. I've been honestly using that to wake up lately because it helps me keep a better sleep schedule.
I was wondering, are you keeping a 24-hour sleep schedule? I think some people say they kind of go naturally to a longer, like a 25-hour day or something. But
so I'm keeping a 24-hour sleep schedule. I'm actually trying to follow the internet a little bit. You?
Yeah. Let's say I'm following 24 hours.
Yeah, we'll say you're following 24 hours. Let's agree with that. But no, I think I would fall closer into a 25 if I let it go naturally. But I'm trying to keep up with the station. I have a few different things scheduled at different times. So.
Okay, great. All right, I think that's all the questions we have. So I want to thank everyone for joining, and thank John and Yuya again for taking the time to talk with us from the South Pole. So thanks everyone, and we'll do it again in a couple weeks. Bye.
Thank you all. Thanks.